This is part 2 in our series of lectures on other forms of induction. And in this lecture I'm going to show you an incorrect proof using the principle of complete induction. The idea is that I'm going to show you a very common mistake that students make when writing proofs using this PCI, and it's a mistake that I want you to avoid making. So here's the theorem that I'm claiming to be able to prove. I'm claiming to be able to prove that for all natural numbers n, 2 to the n minus 1 is equal to 1. So that is clearly something which is not true, and therefore there has to be a mistake in my proof, and I want you to figure out where the mistake is. So here's the proof. We begin by letting S be the set of all natural numbers such that 2 to the n minus 1 is equal to 1, and we're going to use the principle of complete induction to prove that S is equal to all of the natural numbers. We begin with the basis step. The basis step consists of proving that 1 is an element of S, and that would say that 2 to the 1 minus 1 is equal to 1, and that's certainly true because 2 to the 1 minus 1 is equal to 2 to the 0, which is certainly equal to 1. So it does follow that 1 is an element of S. Now for the inductive step, we give ourselves a natural number n, and we assume that this set here, consisting of all the natural numbers smaller than n, is a subset of S, and we have to deduce from that that n is an element of S. So since every natural number less than n is assumed to be an S, it follows that n minus 1 and n minus 2 must be an S, and therefore that means that to say that n minus 1 is there is to say that 2 to the n minus 2 is equal to 1, and to say that n minus 2 is in S is to say that 2 to the n minus 3 is equal to 1. So we have these two assumptions that we're making, and therefore we can rewrite 2 to the n minus 1 in this unusual way, and you'll see that that's actually correct. We have n plus n minus n is n, so we get a 2 to the n, and minus 2 is minus 4 plus 3 is really minus 1. So these two things are really equal to each other, but this one is assumed to be 1 times 1 divided by 1. That is equal to 1, and that proves that n is an element of S. So by the principle of complete induction, it follows that S is equal to the set of all natural numbers, and the proof is complete. So can you figure out where the mistake is in the proof? Well, here's the beginning of the proof. I'm going to, so the first part of it is fine. This is correct. We let S be this, and the basis step is certainly correct. There's nothing wrong with that. But one thing that I would add to the proof is something that I wrote in red. We start by saying let n be a natural number, and what I want you to do is I want you to write this inequality here, which essentially tells you the first value of n for which you don't know that n is an element of S, right? We've so far shown that 1 is an element of S, and in the inductive step we're trying to show that n is an element of S given that all of its predecessors are elements of S. And so let's start by making very clear what is the smallest value of n that we don't know yet is in set S. Okay? So now, since every natural number less than n is assumed to be in S, it follows that n minus 1 and n minus 2 are in S. Well, there's the mistake in the proof. Because if n happens to be 2, which it certainly could be, then n minus 2 is 0, and so it's impossible for that to be in S because that's not a natural number. So there's the mistake. It's simply in writing this thing down. So in order to avoid this kind of mistake when writing a proof involving the principle of complete induction, I want you to do the following things. At the start of the inductive step, I want you to indicate the smallest value that n is allowed to be. In other words, the smallest value that the basis step did not consider. And so that's what I wrote here. I want you to always do that sort of thing. when you're writing your proof of complete induction. And the second thing is you should make sure that your proof is correct even for n being the smallest allowable value. That's exactly where the proof broke down here. When we wrote this, if you would have checked it for the smallest allowable value, you would have realized that you were making a mistake. So make sure whenever you write a proof using the principle of complete induction that you include these two steps here that I've indicated. And note that keep an open mind about the first one, because it's not always going to be the case that the basis step consists of just showing that 1 is an element of S. Sometimes it's going to be necessary for you to prove that a few of the small natural numbers are elements of S. And you're going to see examples of that in the next few videos.